not P at the same time, because that's a contradiction. Remember, there's the law of non-contradiction. So you can't have P and not P. But P, if you're a computer, you don't know, is P going to be true or is P going to be false? You don't know yet, because the query is going to tell you whether you should think it's true or false. So as far as the computer is concerned, P could be either true or false. So P has two possibilities, true or false, right? Well, if I have two statements, P, Q, in any kind of relationship, they could be P and Q, could be if P then Q, could be P or Q, could be P and Q and not P and Q, whatever, right? Any combination. P and Q means that there's now four possibilities, because both P and Q could be true. P could be false, but Q could be true. P could be true and Q could be false, and both of them could be false, right? So if you have two statements, you have four logical possibilities on your truth table. If you have three, notice how easily you can do this. In fact, there's a pattern that you can set so that you're working your way this way, although some people go the other way when they're building their table. I don't actually think that the computer is actually imagining a truth table. It's just doing truth tables as it's figuring out. Here's the code, so there's my table, right? But so if I have three statements, notice now I have double this, right? And if I have four, notice I'll have 16. This is 8, right? And if I have 4, it's 16. 5 will be 32. 6 will be 64, right? You see, the more statements you have in the string of the program, the more content you'll have in your truth table. And this is about the limit of being on the board and doing truth tables as a human. Computers don't have any limitation as far as they might have 50. I don't even, 50 times 2 to the 50 would be the way you would calculate how many lines you would have right in the table. Way more than a human would let me try to do this, right? That would be very boring. But so here we have basically a truth table. If you just have P, Q, and R, notice R is just another variable, right? And you can figure out how many possibilities there are. And so notice if we combine them in different ways, let's see, did he combine them in any specific way? No, not in this one. Oh, okay, he's let's not try to figure that one out. Okay. So you could use truth tables in order to solve a major problem that Russell had. And here's all the statement types, plus you could combine them. So you could see if P then Q and if Q then Q, so they're if P then P and if Q then Q. It's a tautology. It's true in all cases, etc. So literally you could use tables to define arrangements of statements based on the initial true or false of each of the individual statements, and the computer can easily figure out then. By the way, they're not actually talking about computers, they were talking about humans at the time. Remember, computers hadn't been invented yet. Not other than individual humans who were talked about as computers because they were women that were doing all the calculations. I think they were the first computers officially called that. Were French women that were hired to do calculations for, I forget what, but they did calculations. Might have been for the tides, I forget. So, almost missed 5. 5 is propositions are truth functions of elementary propositions. So elementary propositions, these are the elementary ones, and when you add them together in different ways using different connectors, and the number of connectors we have include and, or, and not. Those are your connectors, and, or, and not. And then we can have other connectors. So I can have statement P and statement Q, and I can connect them by using and, or, and I can put a not in front of them or a not in front of a combined thing. So you can use the connectors in all of these different ways as well. And then you can combine the connectors to get things like if P then Q. That's actually a use of 2 connectors. And you can have P only if P. That's actually using 3 connectors. So you can combine them and create still more interesting ordinary connectors, logical connectors that we use in everyday speech that you wouldn't necessarily have simply with just and, or, and not. And by the way, and can include any type of and, like, so I might say but. Your paper is due at the end of the course, but the sooner you get it to me, the easier it is for me to read everything. That's an and. It might have interesting, meaning more than and, but in that case actually just means this is true and this is true, even though I said but instead of and, right? Computers wouldn't make a difference. Okay, so we get all these kinds of combinations. There's a contradiction. Notice in every case the end result is that the statements are all false, and that's contradiction P and not P, and Q and not Q. Ends up being a contradiction all the time, etc. So this worked out really well for making kind of a shorthand work of solving problems in the Principia. And you end up with people very happy with this, at least that we're following it. And 6, I don't think you can actually read. Where's 6? By the way, the Germans made fun of this. They made a song about it. And I won't play it because it's very annoying, which was the point. We're trying to be annoying. Oh, by the way, if you are ever asked, what is the animal name from the Tractatus? The answer is the duck rabbit. Because if you look at the duck rabbit, you can see a duck and you can see a rabbit. Theoretically, you can't see both at the same time, but okay, here's 6. The general form of truth function is, and then you get kind of this not only using P, but he's using Greek letters as well. This says nothing else than that every proposition is the result of successive applications of the operation to the elementary propositions, which that works, that turns out to be the case. Okay. So, that's the end of it. Did we ever see the duck rabbit? What happened to the duck rabbit? Maybe the duck rabbit came up later. Where is it? Did I pass it? I didn't see it. You can ask, where the heck is the duck rabbit? I'm just looking for 7. It's the very end. There it is. Okay. So, line 7, the end of the book. Whereof one cannot speak, thereof one must be silent. spoken like an autistic genius. If you can't say something that's either true or false, or basically a fact, then you have to be quiet, which is totally wrong. Our most interesting things are the things that we can't assign a truth value to, actually. At this point, he didn't think that at all, right? And so he thought, done. I've solved all the problems of philosophy. And so he retired from philosophy and decided to go and he became a teacher. He went to a school for teacher training. And the school, by the way, and this was part of my thesis, by the way, was that the books used were based on the work of John Dewey, like How We Think, for example. And as a result, if anything, he was a Kantian at this point. He'd only really studied Kant. He hadn't really studied, he might have studied Aristotle. I don't know how much he studied. Remember, he was an engineer, not really into philosophy until this happened, right? But once he started reading books on how we think, written by an American pragmatist who was influenced by Hegel, which is an advance over Kant, right? You end up then with this activity of teaching children and assuming that children are not just memorization. You know, you're not just teaching them, memorize this, kid, memorize this. No, you're actually trying to encourage kids to learn things through the ways that you've all experienced in your own education through the American systems, right? Which we, of course, have multiple varieties. We're exploring, the project of education and pragmatism keeps improving, hopefully, right? We keep learning all the time and experimenting, right? Just like the theory of inquiry says. Well, if you're teaching the theory of inquiry to children, you're going to be thinking differently than this. And after this period, this experience, which involved him also being captured during World War I, he ended up in an Italian prisoner of war camp. Remember, he was Austrian, so he was fighting in the artillery for Austria. He was captured, ended up in a prisoner of war camp where he finished this book, actually. But after his teacher training and his time spent, sorry, that was confusing how I did that. But he ended up getting kicked out of an Austrian village school because when you have an autistic genius, he literally knocked one poor little girl out in class. The farmers chased him out of town with pitchforks. He had to run for it. That's not just a metaphor. He literally had to run for it. So that wasn't a good profession for him. After that, he spent about a year building a house for his sister, which, by the way, is still there. It's a museum because it's so odd. Such an interesting example. He designed every little bit, including like the door latches and stuff, to be as simple as possible. So it's kind of, I should show you the Wittgenstein house.
Looks like a Sim house.
It looks like a what house?
A Sims house?
A Sims house. Because it would have been drawn just by a computer for your design, right? Interesting. You can go in as well. I think this is those doors don't look like he did those. However, you can
Are those bars?
I guess panes. Those are glass panes, right? So By the way, the house ended up being used by the commies when remember it was the Soviets took over for a while, 20 years, I want to say, maybe longer, and they used it as like a communist office headquarters, but it's now back to being a museum as opposed to